Consider the following situation. There is a densifiable layer, in fact, a fairly loose sandy stratum, which may be somewhere between 10 and 15 meters of depth, so that it is very difficult to change the properties of that layer in a very extensive plateau or valley like the one that you see here, using techniques such as deep dynamic compaction. So one may wonder whether blasting that layer will eventually increase its density to values that will prevent liquefaction. We did that at this site, and the ground settled quite a lot, in fact, probably several inches, and post-blasting tests show that it was still liquefiable. And then we did a second round, the third round, the fourth round, and we still believe that the layer may remain liquefiable at certain locations. So the question is, how many blast densification cycles do we need in order to prevent the liquefaction of this layer? In other words, in order to obtain sufficiently high dense formation. Of course, liquefaction is a complex process, and in every cycle of liquefaction, all the upper layers resediment. So only the lower layers actually get denser, and the upper ones are, once again, being resedimenting like a freshly deposited soil. But still the question remains, how many cycles do we need to do? So consider in this case a typical shear versus confining stress in the PQ space, in which we have unfolded the volume, the void ratio, and on the fourth axis, we are showing the deviatoric strain. You may refer back to earlier presentations where we were talking about the critical state of soils to refresh this diagram. So what it is, the projections of a fourth-dimensional space onto a plane. In the upper quadrant, we have the tau sigma space, in this case in terms of Q and P. And in the lower diagram, we have the evolution of void ratio with confining stress, which will be the projection of the critical state line on EP prime. Now imagine that we produce the following cycles, as shown on the upper diagram, where we confine the specimen under drain conditions, and then we apply some deviatoric load, and we cycle around that obliquity, initial obliquity, up and down in deviatoric mode. On the void ratio projection, most likely this material will get denser and denser and denser, going towards an asymptotic value. The voids cannot totally vanish, and so at most it will go to zero, but clearly that will not be the case unless there is total crushing of the material. So this will go to an asymptotic void ratio. Now on the deviatoric component, the shear, the deviatoric load, the shear versus the deviatoric strain, this could continue accumulating shear, or it could reach an asymptote where there will be no more shear accumulation. When there is continuous shear deformation accumulation, we call that ratcheting. Like a ratchet, when we tighten a screw, we go back and forth, accumulating rotations. Conversely, when it reaches an asymptotic value and there is no more accumulation of shear strains, we call that a state of shakedown. So it appears that there will be two limiting conditions, one for volume and the other one for shear deformation. For volume, we are looking for a terminal void ratio, terminal density. For shear, we wonder whether there will be continuous accumulation of shear deformation or not. And this could be questioned in many different conditions. For example, what happens if the water table goes up and down, and so the effective stress changes, and in so doing, the isotropic stress, in so doing, it may bring us closer to failure and changing the obliquity. Or if we have axial extension, axial lateral compression, it could be just a case of pure shear or a case of axial compression and unloading. So there are different possible dimensions, and the other one could be that we could be moving on a K-naught line under zero lateral strain conditions. So let's explore this one, and we have to recognize that the horizontal stress will be changing, and so the K-naught line itself will not have a constant obliquity per se. But in this case, we are not wondering about the accumulation of shear deformations, we are wondering about the accumulation of volumetric strain. So this is the case that we are going to show you some data. This is a floating ring oedometer. This is where the specimen is contained. And we mount bender elements so we can also monitor the evolution of the small strain shear stiffness. The advantages of using a floating oedometer cell is that we minimize the side friction very significantly, as you may remember from previous analysis. Otherwise, there is an exponential decrease in the vertical stress. So this is a typical loading path. We're going to go in steps, loading to different vertical effective stresses. And then once we reach a certain stress, we're going to oscillate vertical load with a certain frequency. Now we have to be careful because this may require millions of cycles. And so if we wait a long time between each cycle, then the duration of the test is prohibitive. However, if we do it with very periodic cycles, let's say every 5 hertz, 5 per second, there is no time for the specimen to relax to the next condition. So we will have to optimize the frequency in order to conduct very large number of cycles. And if you go back and see what are field conditions, then we see that, for example, in the case of machine foundations, the number of cycles, the frequency of the cycles may be high, but they may be very low for the case of sea waves or storms. With that in mind now, let's explore some examples. This is Ottawa 2030 sand. This is the most classical sand in geotechnical testing, and it's placed in an oedometer both under loose and dense conditions. We do the monotonic loading, and then we start doing 10,000 cycles. Notice that there is maximum stress, and then there is an oscillation of that stress, and these two parameters will be important. As you can see, the specimen that was loose is contracting much more than the specimen that was dense. The vertical scale, the range of the vertical scale is the same in both cases. However, we have shifted the axis because one is dense and the other one is loose. If we put each one of these cycles, now we stretch it and we plot the change in void ratio versus cycles, we're going to see a very classical decay towards an asymptotic value. And that is what we're going to show next. But before I move on to the next slide, notice that we are plotting the data with the third decimal because this is a sand in an oedometer test. The deformations are indeed small. That would not be necessarily the case of clays. So this is a typical data set, and you see that both the loose sand and the dense sand deform quite a lot at the beginning, but the formation continues even after 10,000 cycles. And now we can fit an equation of this form, an inverse power equation, where when the number of cycles I goes to infinite, then this whole factor goes to 0, and we have reached the terminal void ratio. And that's an important parameter because we may not know in detail what happens in between, but asymptotes lead to very robust engineering designs. So this is an important parameter for us to determine. The other one is what is the value n, where this whole ratio is 1. That means when n is equal to I minus 1, or when I minus 1 is equal to n, this is the characteristic number of cycles where the deformation that has accumulated would be the same as the range of the deformation to terminal void ratio divided by 2. So how many cycles does it take to reach half of the volume contraction that would take to go to terminal void ratio? And so this is a very good equation. This is the one plotted in red here and blue in the lower part. And you see that indeed the data follows that line very nicely. Now I'm plotting this in logarithmic scale. So we can see, once again, the first few cycles are stretched out, the last few cycles are contracted, and you see the trends more clearly. And it will be about 350 cycles for the loose sand, 200 cycles for the dense sand, for this value of n asterisk, which is the characteristic number of cycles at half the final contraction. But also notice that we can resolve the terminal void ratio very precisely. And we can fit the lower and the upper bounds, so we can also compute what is the amplitude of the elastic strain, and then use these equations to anticipate the accumulation of plastic deformations as well. This data set corresponds to sands with different amount of fines, from 0% to 100% fines, sand-silt mixtures. And as you can see, for each data set, we can fit the equation I shown here in yellow and determine the terminal density in each case, but also the number of cycles to have the volumetric contraction. So for the sands with a large fraction of fines, it takes a very small number of cycles, but the deformation is going to be slower but more persistent for the sand without fines. Also notice that in all cases, it takes a fairly large number of cycles. It's not just the first 2 cycles or 10 cycles like has been suggested in previous studies. This is the same case now shown in terms of volumetric strain, and the volumetric strain continues accumulating, but you can also see the hysteresis that is taking place. I'm going to show you some individual cycles to make it clearer. At the beginning, there is lots of hysteresis, and the distance between 2 consecutive cycles is the plastic strain that has taken place. The elastic strain is the one that is giving us this slope of the cycle. And we can recognize that the hysteresis is decreasing with the number of cycles. And even though I cannot see it here, there is continuous accumulation of deformations, and that is the one that gives me the accumulation to 10,000 cycles and beyond. The case for the dense sand is very similar. If you go back to the previous slides and you see the amount of strain that is taking place and the accumulation of volumetric strain, you have to wonder how is this related to the typical concepts of threshold strain used in earthquake engineering, from Mishihara to Vucetich and Dobry, for example. Well, to our surprise, the deformation that is taking place is much, much smaller than the elastic threshold strain that was anticipated for sands. In other words, there is accumulation of plastic strain even under very small elastic strains imposed on the material. It gets to a point that when you do the calculations, it appears that the relative displacement between 2 grains is smaller than 1 angstrom. And you say, well, but there has to be about 1 angstrom displacement in order to break bonds to cause frictional displacement, shear displacement. So what is actually taking place is not every particle moving relative to every particle. It appears that bunches of particles are gradually moving relative to each other. Now, what happens with the shear wave velocity? In other words, the measurement of the instantaneous shear stiffness of the skeleton. Well, it is systematically increasing with the number of cycles. For example, here in 4 cycles, in 4 log cycles, it has gone from 20 to 30, let's say 36. So it has gone 9 meters per second per log cycle. So it is not a very large amount, but it's systematic and it continues increasing. And so contacts with the number of cycles, maybe with some fretting at contacts, even though the displacements are very small, the contacts are getting more and more stable and flatter. So the shear wave velocity, it continues increasing. This is a form of mechanical diagenesis that may take place in our geological systems throughout the millennia, giving rise to the aging of sands. So the shear wave velocity, now if I plot it versus effective stress, during loading, the shear wave velocity goes up with a fairly high beta coefficient because this was a loose sand and this is the dense sand. The beta coefficient is smaller. However, during the cycles, basically we are reporting it at mean stress of the cycles, it goes up a little bit and then it becomes more stable. So the exponent at the beginning was 0.225 and then it goes to 0.200. And the same happens with the dense specimen, all indicating that the skeleton is becoming increasingly more stable and more rigid with the number of cycles. These exponents, alpha and beta, plot along the general line of the inverse relationship between higher sensitivity to the state of stress, beta exponent, and lower alpha factors. In other words, the velocity, if I extrapolate this to 1 kPa. And this is the relationship in different forms that we have shown in previous presentations. Once again, if we put the values that we had mentioned before, the increase per log cycle, now I normalize by the initial velocity in the first cycle, then I see that the rate of increasing velocity per log cycle is 1 to 2%. The higher the stress ratio with respect to the initial stress, the more pronounced this increase will be. And there is this transition between the exponent of these lines with respect to the initial shear wave velocity of the sand. Now, what happens when the number of cycles is either very, very high, we're approaching the million, or when the stresses are very high? On yellow here, you see the monotonic deformation of this sand, and somewhere here will be the yield stress, 10, 15 megapascals. When massive crushing is taking place, small fines are being produced before that. And here you have 5 tests in which we have loaded the sand to values before yield and cycle, or values that exceed yield followed by cycles. And as you can see, as soon as you exceed yield, the accumulation of volumetric strain increases quite rapidly because of contact failure and accelerated fretting at contacts. And if we plot a test with a large number of cycles, before I had shown you up to 10 to the 4 cycles, 10,000, now let's extend that to 1,000,000 cycles. Now something interesting happens. The original trend, now there is a deviation. There seems to be a tipping point, which can be somewhere between 10,000 and 100,000 cycles for the materials that we have tested, where the accumulation in logarithmic scale begins to increase, indicating contact fatigue. We can take a look at a large number of data sets that we have created. Each of these points is a test, a full test with a large number of cycles, and we plot all the data and trying to normalize it, plotting the initial conditions in terms of relative density, the standard relative density, using Emax and Emin as reference values to superimpose different sands being tested here. And then for each one of them, we determine the terminal void ratio. And now we can plot the change in void ratio from the initial condition to the terminal void ratio, also normalized with respect to Emax and Emin. And so this double normalization of the initial condition and the terminal condition allow us to collapse all the data onto single trends, where each trend reflects a different stress change per cycle compared to the initial stress in the cycle. Conclusion, the higher the stress change versus the initial stress, the lower the terminal density will be. In other words, the higher the volumetric changes to reach terminal density. But there is another corollary of plot that each initial condition, each sand at each initial relative density and subjected to its own stress changes will reach a different terminal void ratio. So the terminal void ratio is more complex than would be, for example, critical state. Each material and process will have its own terminal void ratio. Critical state falls into this overall summary, and critical state represents the terminal void ratios under monotonic shear. So talking about shear, now let's see what happens when we subject the system to shear. And now we have not only the volumetric contraction that takes place under zero lateral strain in an oedometer, but we're also going to experience the accumulation of shear loading. So we do this in a simple shear device, also with bender elements mounted on it. And we are going to apply the load in steps, the vertical loading. Then we're going to impose a deviatoric amount of shear loading, which is going to bias the accumulation. And from that deviatoric amount of shear, we're going to start the cycles of shear stress. So this is what we obtain. This is two cases of relative density. This is 49 and this is 25% relative density with different deviatoric loadings. And we see that we have not only the accumulation of volumetric contraction, but we also have the accumulation of shear strain. For shear strain, now we identify another model. We try to look for models with a similar family of curves, but we had to add a linear accumulation function. Why is that? Because very loose specimens under high deviatoric load are going to accumulate shear deformation forever. So the lower material here is experiencing ratcheting, the upper material is experiencing shakedown. And in order to capture ratcheting, we use the D parameter in this additional linear accumulation function. And as you can see, here we have the diff value, which is the plastic strain accumulated in every cycle. And in the upper one, that value goes to 0. That means that there is no additional plastic strain accumulation. We have reached shakedown. So to summarize all the data sets, and we tested materials starting from contractive and from dilative conditions, as the material approaches failure, this is normalized now the peak shear stress. So this takes into consideration the static deviatoric shear stress plus the cyclic deviatoric shear stress, normalized by the shear stress at critical state. As specimens are approaching this value, the likelihood of ratcheting increases. Now, if the materials were on the contractive side, the probability of ratcheting increases as we approach that ratio of the critical state. However, if the material was dilated, ratcheting will happen when we exceed that value. We have to go towards the peak. As a take-home message, the probability of ratcheting increases as we approach and or exceed critical state in the peak of the shear loading. Now, what happens with the shear wave velocity? Similar trends to what we saw before. As the number of cycles increases, the shear modulus from shear wave velocity increases. However, the shear modulus that we can compute from the repetitive loads goes towards an asymptote. So this is the shear modulus computed peak to peak. This is the shear modulus computed from Gmax. And this is the drop in the shear modulus when the material is ratcheting and the fabric is not going towards a stable asymptotic condition. So it doesn't increase continuously. In fact, it begins to drop. So what is going on behind all this? Well, we initially pack the material, and then when there is shakedown, the material gets denser and denser, and eventually the grains maintain their neighbors and the contacts begin flattening. However, when the material is ratcheting, grains continue exchanging neighbors, and there is no flattening of contacts per se. Therefore, small strain shear modulus doesn't reach an asymptote, doesn't increase. In fact, it may actually decrease. Now, there are other mechanisms that could increase the deviatoric loading and may also lead to accumulation of volumetric and deviatoric strains. So consider the case that we have a triaxial cell confined under sigma 1, sigma 3 effective stress. So we have followed a monotonic loading with confinement, then we apply a deviatoric load, and when we sit at this point, we decrease and increase the internal pore pressure to create the cycles. So this was with back pressure saturation, and so now we decrease and increase, and that means that we are varying the obliquity of the stresses in these conditions. And that means that we are also varying not only sigma 1, but also sigma 3. Let's look at some of the data. This is a little bit of a complex plot because we are showing the whole data set, which is the isotropic confinement, drain, the deviatoric loading, then the cycles of pressure. And at the end, we conclude the test by a monotonic and drain conditions. So notice that we start the test 1, it was very loose, and we go to different conditions, and starting from below critical state, in other words, a dense test. In all the cases, there was accumulation of volumetric strain, and then when we close the valve at the very end, the specimens show different tendencies to build up positive pore pressure or negative pore pressure for the very dense specimen. Now, not all tests contracted. In fact, when we started with void ratios which are very low, in other words, materials that are dense, towards E minimum, well, these ones are towards E maximum. I will show you an open scale in the next slide. So some of the materials during deviatoric loading and depending on the maximum stress obliquity that we reach in the cycle, some of them contracted, but some of them dilated. And here you see them projected on the P prime void ratio space. This is the starting point, the open points, and you see where they ended after 100 cycles, some of them experiencing contraction, even what appears to be beyond the critical state line, so becoming very dense in the cycles, while with those that started under very dense conditions actually dilated towards a critical state condition. Now I open the scale to show you in reference to Emax and Emin where was the range of the specimens that were tested. The cumulative deviatoric strain also was proportional to or strongly related to the maximum obliquity that was reached in every cycle. As the obliquity increased, the deviatoric strain also increases. Please notice that this is a very high obliquity because the obliquity at critical state for this sand is 0.52. So this was indeed approaching failure conditions, explaining why there is such a pronounced accumulation of deviatoric strain. So what are the main takeaways from monotonic loading? Repetitive loads are everywhere in nature and in our engineering systems. The following sequence of presentations will show you other forms of repetitive loads. It is strongly related to the hysteretic response of the soils and the emergence of nonlinearities. Now, what is important is that concepts from monotonic loading may not necessarily apply to repetitive loads. Case in point, remember that there was volumetric strain accumulation, and also there will be deviatoric strain accumulation, even though the cyclic strain imposed on any cycle may fall below what appears to be the elastic threshold strain from earthquake engineering point of view. From a volumetric point of view, regardless of the loading path, every soil for every process will reach a terminal density or a terminal void ratio, concept that comes already from Casagrande in the 60s. Now, interestingly enough, I didn't highlight it earlier in the presentation, the terminal void ratio does remember the initial void ratio. And furthermore, the terminal void ratio can cross the critical state line to go into very dense materials. So you may start from very loose, but by shaking with small strains, the specimen densifies beyond the critical state, and that is not surprising. After all, that is the way we densified sands towards the minimum void ratio. The Emax and Emin, as we have discussed before, are determined by grain size distribution, and particle shape. So they capture a very profound parameters, very important parameters that determine the behavior of sands. So Emax and Emin are great parameters for normalization, not only for the initial conditions, but also for the terminal void ratio. From a shear point of view, the material may stabilize and don't accumulate shear anymore. That is a state of shakedown. Or the material may continue accumulating deformations in every cycle. That is ratcheting. And as I mentioned earlier, the threshold strain may be smaller than the elastic threshold strain that we had come to acknowledge in the earthquake engineering literature. When does a system go to ratcheting? When the peak stress during the cycles approaches the critical state or the Coulomb envelope. Otherwise, there is a good chance that the system will evolve towards a shakedown condition. Please notice that the peak shear stress will have to exceed the critical state of liquidity in order to lead to ratcheting conditions in dilative soils. There are several publications that have come out from our group. A couple more are in progress, but there are also wonderful data throughout the literature, including the data by Wichmann recognized in this slide.